All right. All right, everybody. Welcome again to another fun discussion here, continuing our discussion on waves. And so continuing here to think about our oceans and the impacts that they have on this Earth system in talking about long waves. Now, waves with incredibly long wavelengths. All right. So in this lecture, we're going to be talking about, or we're going to be setting the stage for talking about tsunamis and tides and those sorts of things, certainly addressing tsunamis and hopefully reshaping our thinking about these events as being something like this heavily photoshopped image here, but rather rapid increases in sea level associated with energy being transmitted through the ocean, oftentimes because of geological events. And so we're talking about this group of waves, right? This umbrella, the long waves, waves with these long wavelengths. So we're going to, again, define what a long wave is, what makes these waves unique, what causes them, right? What are the disturbing forces, right? We remember the restoring forces of these waves are going to be things like gravity, right? But the disturbing forces for these different waves can vary. We're going to talk about then again tsunami. We're going to talk about some famous tsunamis, right? Things that you may have heard about in the news. If you've ever wondered what was the biggest tsunami, we're going to answer that question for you here today. And then we're going to talk about how we prep for them. All right. So long waves, also sometimes referred to as the great waves, These long waves have incredibly long wavelengths, right? Incredibly long wavelengths. Again, notice that we're not describing these great waves in terms of their height, right? Not the distance from crest to trough, but rather their wavelength, because that long wavelength, to generate these waves with this long wavelength, takes a lot of energy, and thus these waves can move at incredible speeds, and on occasion can be destructive. They're not always destructive. Not all long waves are destructive, but they can be. And certainly in instances of tsunami, that's an example of a destructive long wave. So let's talk about the disturbing forces for these winds. What causes them, right? A bunch of things can cause these long waves. Low pressure systems, right? Low pressure systems. That is areas where that atmosphere is rising, right? Decreasing atmospheric pressure, along with wind, can most certainly cause long waves, right? That is, if you get a steady wind blowing over an area, right? A steady wind, particularly over an area that's in a confined basin, right? The Great Lakes are a great example of where you might get this condition. That long blowing wind will actually take some of the water and cause it to pile up on one side of the lake basin. So again, this isn't wind just being really strong and building big waves. This is wind taking and building up that water such that it has an elevated height on one side of those enclosed basins. We're going to see an example of that here in just a minute. Sudden water displacement, right? Sudden water displacement is another one. And what I mean by that is if you have a bowl of water, right? And you wanted to go ahead and make yourself a delicious bowl of soup, and you took all your ingredients and just suddenly plopped them into that bowl very quickly, you're displacing water in that bowl, right? And you'll cause it to move, right? And if you picture that bowl as the size of the ocean, right? And those ingredients are the size of a mountain, you can imagine the amount of energy involved with something like that, right? So that sudden water displacement, that's how we oftentimes get our tsunami. Rocking water in a confined basin, right? Rocking water in a confined basin, that's in line with exactly what we talked about with our buildup of water elevation via wind blowing across these basins steadily over time. And then gravitational attraction, right? And what we're talking about there are the tides, right? Primarily the tides. So that is gravitational attraction and interaction between gravity here on Earth, the moon, and the sun primarily. And we're going to talk about that in greater length when we talk about tides during a separate learning module here. All right, so let's take a look at some of these types of long waves then that are associated with these various disturbing forces. So storm surge. Storm surge, that's something we talked about when we talked about hurricanes, right? That near sea level, right, you raise sea level via decreases in atmospheric pressure and wind from a hurricane, piling that water up on shore. So underneath that system, you will have a little buildup, a little mound of water, essentially a wave crest, right? And on either side of that wave crest, right, at about maybe sea level or so, you can consider that to be a wave troughs on either side of that crest potentially. But they are not true, or this is not a true wave because we don't see a measurable wavelength within this storm surge. So sometimes we bring this up here because sometimes storm surge is mentioned in the discussion of long waves because it has essentially a crest to it, but it's not a true wave in that it does not have two wave crests that you can utilize to measure that wavelength, right? And so storm surge, again, sometimes pops up in these discussions of long waves, but in reality, it's not really a wave without having that measurable wavelength to it. All right? All right. That second term there, seiches. A seiche is that rocking water in a confined basin. All right, we're going to see an example of that here in just a minute. So again, we mentioned this previously, that a seiche or these sorts of waves can operate almost like a seesaw or a teeter-totter, right? And that's how the water moves in a seiche, but we're going to see that it's actually a wave. Tsunamis, right? Again, our sudden water displacement, and then tidal waves we're going to discuss in our next lecture. So we're going to take a more detailed look now at each of these items, right? So storm surge, right? Again, in storm surge, we've only got one wave crest, right? So again, here is the buildup of water here under the eye of under the storm here. Part of that driven by changes in atmospheric pressure, right? But the majority of that storm surge generated, that elevated bit of water below the storm generated by winds within the storm there. Again, that's one wave crest, right? You've got one wave crest here. There's no measurable wavelength, so not considered a wave. While both low pressure and wind are playing a role there, again, I want to stress that it's mostly wind that's doing the job, right? That decrease in atmospheric pressure there, as per this image, is showing maybe it contributes to about 5% of that total storm surges by that atmospheric change alone. This dome of water, right? Essentially, this single wave crest is comparable in general to the diameter of the storm, right? So the width of this dome can maybe be 100 miles or so on average for a hurricane. That's a really big change in sea level topography. And so that change in sea level, right, is then reflected over an area that's at least that big, right? That means that a 100-mile stretch of the coastline will see relative sea levels change as this storm passes by as a result of both this wind and pressure-driven surge. That huge area that this impacts, right? That huge area means a lot of people are potentially exposed to this hazard. And this is indeed, as we mentioned when we talked about hurricanes, this is the cause of the largest loss of life associated with things like hurricanes, tropical cyclones in general, right? And that is a lot of people live very close to the coastline, such that when this sea level rises, their homes, their workplaces, the places that they recreate become flooded. And the water that this brings is oftentimes moving very rapidly and can cause all sorts of death, damage, and destruction. There's another interesting thing that this storm surge can do that can cause some real problems, and that is it can kind of team up with the tides. Storms and their movement are moving, or these tropical cyclones are moving because of atmospheric conditions, right? Wind is moving these things around in the atmosphere, right? And so they don't really have any relationship to the same forces that cause our tides. But every now and again, the stars can align to where this storm surge, the peak of this storm surge, can be aligned with maybe a high tide, right? So tides, right? That change, that daily change in sea level during the day, you may have a period of higher sea level related to the tides. If you add to that storm surge, now that storm surge's reach can be much further inland. And as a contrast to that, every now and again, we get lucky and that storm surge can be paired with a low tide, in which case that storm surge is going to have less of an impact, right? So it's a bit of a roll of the dice there, but again, certainly the timing of those storms and how they align with the tides is an important set of factors in determining how destructive this storm surge might be. All right. Seiche now, seiche, or standing waves, standing waves. Standing waves. These are waves which oscillate vertically. There's no horizontal movement, right? So again, this is very much like a teeter-totter or a seesaw. That is, in places like the Great Lakes, right? You may have a steady wind blowing across the surface of that water for a long, long time. And given how large that area is, that lake may be, or that confined basin may be, that wind in blowing in that steady direction takes water from one side of the basin and piles it up on the other side of the lake, right? That wind piles it up. And as long as that wind stays blowing, right, as strong as it was or stronger, that water will stay on one side of the basin at a higher elevation than what we see on the upwind side of the basin. All right. So that's what we're seeing here in both of these images, right? Is we imagine here that in this image, the wind is blowing steadily from left to right. And so that water builds up, right, on the downward side of that basin, right? So we get this buildup of water there, right? And then we get this drawdown of water on the other side. So that water is moving its way across the lake. Notice that in the middle here is something called a node, a node. That node, right, is sort of the pivot point for our wave seesaw, right? And that node, the elevation of that node would be the lake or the basin's elevation, right, if that water was flat, right? So at that node, right, comparing the elevation of how high the water has gotten, right, and how low the water has gotten, we can see how much water has built up by comparing those elevations to the elevation at the node, right? And so all of that water then, all of that water that is built up to an elevation that's higher than the node, right? As soon as you start to back down that wind strength, as soon as that wind starts to weaken, now you don't have that mechanism to hold that water in place. So it comes sloshing back across the basin, right? And will come sloshing back across that basin and will raise elevations of that water on now the upwind side of that, or what was the upwind side of that basin, right? Because of all that potential energy that's been built up in this higher elevation water here. That, again, in our seesaw, the rotation here, right, of our seesaw, the lifting up here will occur again about that node, right? That rebound, that run-up elevation on the other side of the lake or the basin may not be quite as high, right, as what we saw in the buildup elevation there, right? But it still can be pretty considerable. And so this will take a little bit of time and likely multiple oscillations for it to eventually settle out and stop. These seiches, not in general, in places like the Great Lakes, are not particularly destructive. They are aware that these things occur, and so they attempt to build appropriately with appropriate setbacks from the lakes as they can. Generally, when you see videos of these seiches, you'll see that they're on time lapses, and the rise and fall of lake level as these seiches settle out takes a little, or is a little bit of a slow process that if you were standing there, you might not even recognize, right? Where you might see more considerable seiches is in a swimming pool during an earthquake. The movement of seismic waves through something like a swimming pool can have this same effect. And you may have seen video from our recent earthquakes. You may have seen videos of water sloshing around in the swimming pool there in this standing wave type fashion, right? Those waves in a swimming pool aren't necessarily going to be destructive to the community, right? But they can result in a lot of that water splashing out of the pool and some pretty breathtaking imagery to go with that. So these seiches, again, can be caused by wind, right? And they can be caused by that seismic activity. They can also be caused by pressure changes through very similar mechanism as we discussed for hurricanes, changing the elevation of water. We can do the same thing here in our confined bases by changing atmospheric pressure on one of the sides of the basin here. And again, getting that teeter-totter type flow. That's the big takeaway here for seiche, right? Is that lack of forward movement. Rather, we get that oscillatory movement. What we see over the top, you might think, well, Sappenfield, that's not a wave then either. How do I measure the wavelength then, right? I only see, in this image, I see one crest and one trough. There's no wavelength there. Well, what you're seeing is that energy pass through this point. And if you were to map out this oscillation through time, that's what this blue line is representing here above, is we would see as this rose, that's our wave crest. As it falls, then we get our wave trough, and then it rises again, another wave crest, another wave trough, until that system is done. So we certainly could measure the wavelength in this setting. All right, so a true wave there with our seiche. All right, but let's get to maybe the star of the show, tsunami. Tsunami. That term, tsunami, means harbor wave. You might also hear these referred to as seismic sea waves, and that's because oftentimes what's involved in generating a tsunami or also experienced around a tsunami are things like earthquakes. Tsunamis are really long wavelength, shallow waves, really long wavelength, shallow waves, right? We mentioned during our introduction to this waves topic that we can classify different waves as being shallow, intermediate, or deep based on a comparison of their felt depth, right, to their wavelength. These waves have wavelengths that can be multiple hundreds of kilometers in length. Our deepest points in the ocean, right? Our deepest points in the ocean are only kilometers in length. Or in depth, excuse me. So there's just simply not enough room in the ocean, right? Even though these waves are passing through that entire body of water, there's simply not enough depth in the ocean for these things to be classified as anything other than shallow waves, right? And so how do we produce these waves? Well, here is the rule for generating tsunami. You got to have that water displacement. You got to have water displacement. You got to move some water, right? You got to move some water. And how do you do that, right? How do you move large amounts of water? Well, oftentimes that requires geology. Oftentimes that requires the movement of tectonic plates, right? So we can displace, as we mentioned previously, we can displace huge amounts of water in a variety of ways, right? Huge bodies of rock falling into the ocean displaces lots of water, can generate a tsunami, right? But it's not all about rock. Glaciers can generate tsunami too. As glaciers calve into the ocean, that is, as ice falls off of the end of the glacier into the water, it too can displace large volumes of water and generate really significant tsunamis, particularly since glaciers oftentimes spill into the ocean in very fairly narrow canyons. The calving of a glacier can have, or it can generate a wave that can have significant impacts within those confined basins. But some of our largest tsunamis, right, and maybe our more frequent tsunamis are generated by the movement of tectonic plates. By the movement of tectonic plates, earthquakes, right? That is the energy generated during this movement oftentimes also generates an earthquake. But I want us to know that the earthquake itself is not generating the tsunami, right? The earthquake itself, that is those waves that we feel as the earth shakes, right? It is not those waves moving through the water that generates the tsunami. Rather, it's the reshaping of the seafloor that generates the tsunami. You may remember when we talked about plate tectonics, we talked about convergent plate boundaries, and that at convergent plate boundaries, you'll see one plate subducting below another plate, one plate subducting below another plate. And as they do so, that overriding plate, right? That overriding plate, in this image right here, we've got our overriding plate. Here's our subducting plate. That overriding plate there gets a little bit of a flex to it. There's friction between these two plates, and that overriding plate there is then sitting flexed. Eventually, when the integrity of the rocks between these two plates fails, we get what's called rupture. And when that boundary ruptures, what happens is that boundary, along with those portions of the plate near the boundary, completely change shape. That overriding plate will lose some of that flex, right? And we'll also see a reshaping of portions of the seafloor there adjacent to that plate boundary. It's that movement that can change the shape and displace huge volumes of water. Some of these ruptures can extend for hundreds of miles in length. That's a huge volume of water that's being moved by plates by plate boundaries that, again, are changing shape by sometimes tens of feet. It is a remarkable amount of water, and that is commonly how these events start. And so the majority of our tsunamis, they happen in the Pacific, right? So here's a map showing a few tsunamis here all around the world from our textbook there. So there's some of the events, and we notice, wow, they really are concentrated in the Pacific. Why? Well, thinking back on our plate tectonics lecture, we know why, and that's because much of the Pacific Ocean basin is surrounded by convergent plate boundaries. We see convergent plate boundaries all over the place around the Pacific, right? And that results in a relatively high frequency of these events. These waves can travel tremendous distances across these entire ocean basins, right? And so again, anywhere adjacent to oceans containing this sort of plate tectonic setting, right, certainly at risk for tsunami hazard. All right. Awesome. Awesome. I really want you all to make sure that you're understanding that mechanism, that flexing up of the overriding plate there at this plate boundary. If you're not understanding that, no worries at all. Give me that email or show up to our live lectures or whatever works for you. to ask the question. And we can go through that again and make sure that we find the analogy or the image or whatever you need to make sure that you understand this concept, because it's a really big one for the remainder of our discussion in here. All right. Awesome. So let's take a look at what happens during a tsunami. When you're out, when a tsunami is generated, if you were out in the ocean near where that tsunami may have began, right? So out in the deep part of the ocean, you may not even notice the tsunami going by, right? And that is because that volume of water has plenty of space available to it for all of the orbits within that tsunami, right, to be held in that body of water, right? So on the open ocean, you likely wouldn't even feel this event passing by, right? In and among all the waves from the wind and everything else, it might seem pretty indistinguishable. But again, these tsunamis have orbits that will extend from the surface of the ocean to the sea floor. So what happens is, as that sea floor, right, as the depth of the ocean changes, as things get shallower, as we discussed when we talked about wind waves, same thing happens with tsunami in that those orbits start to interact with the sea floor. There's some friction that's experienced, right, which causes the wave to grow and steepen as it approaches the shoreline. But again, these waves have a tremendously long wavelength. So that image that we started this lecture out with of the towering barrel over the city there, not necessarily accurate, right? Not necessarily accurate. And in fact, what oftentimes happens when a tsunami is approaching is that the water recedes very quickly. Very quickly. That is, standing at the shoreline where a tsunami is approaching, you may see portions of the coast there that are never exposed, even during very low tides. This can be so sudden, so fast that it leaves things like fish flopping around. That can sometimes be interesting for people if you didn't know what was coming. You're looking out at the ocean and all of a sudden the water is running away very quickly, right? And there's fish exposed and maybe some shipwrecks or whatever the case may be. Makes you want to kind of go out and visit and see what's going on. Well, that's what you don't want to do. That's the dangerous place to be, because then on the back of this comes the wave crest of the tsunami. And so the wave crest of the tsunami is typically represented by a very rapid rise in sea level. A very rapid rise in sea level, oftentimes coupled with what appear very similar to extremely large wind waves, as that energy then progresses then onto the shoreline there. So again, that very rapid rise in sea level is reflective of that wave crest of the tsunami. And so what we see is that that tsunami water level reflects the height of the tsunami. And that height of the tsunami will impact first, right, how high in elevation that tsunami might reach, right? How high that tsunami might reach, right, as compared to normal sea level, to how high it actually reaches there on land. We call that the run-up elevation. The run-up elevation. And notice that that run-up elevation is a little bit lower than the tsunami water level there, right? That run-up elevation is how high up on land that tsunami actually gets, right, in terms of elevation above sea level, which again is impacted by, or which we may think or may recognize is impacted by friction and things as that wave moves across the land surface. All right, so that's our run-up elevation. How far inland, right, that tsunami actually reaches, we call that the inundation distance. And that inundation distance is going to be impacted by things like the shape of the coastline, right? Is it a very gradual coastline with not much slope, or is it a very steep slope? Is it a very steep slope, or is it more of a gradual slope? Very steep slopes are going to have a lower inundation distance, whereas very shallow slopes are going to have a greater inundation distance. All right. Awesome. Awesome. Hazards like this, tsunamis, can result in incredible amounts of death and damage and destruction. And why? Why are these things so impactful? What makes a tsunami so impactful? Well, there's a number of reasons why we get such high body counts during a tsunami. The first one there is that many people do not receive warning of an approaching tsunami, or the warning that they do receive does not provide an adequate time to get out of the way. We do, and we're going to discuss tsunami warning systems here. All around the Pacific Ocean are buoys and things that help to predict tsunami. But it is not the case that everybody is tied in with that system. That is emergency prep, right, of being able to provide the communication of an approaching tsunami has not yet been completed for a lot of portions of the world. So people, even in the wake of as these events are imminent, have no idea that they're on their way, or have had that and no idea in the past. With cell phones being so prevalent and things, certainly those communications have improved, but there's still a long ways to go. Especially when you think about that these tsunamis oftentimes are traversing an entire ocean. So you might think, well, if I felt an earthquake and I was in an area potentially exposed to tsunami, I would just do what I needed to do to get away from the tsunami. But it's not always the case that you feel the earthquake, right? So even that natural warning system isn't there, especially if that earthquake occurred across the entire ocean. You're not going to feel it. So you're not going to receive that natural warning as well. And just like earthquakes, because these events that cause these tsunamis are often tied in with the same sorts of events that cause earthquakes, these things are largely unpredictable. They're largely unpredictable, right? We can't say when the next one's going to occur. We can just identify where this hazard exists for different areas. It's also a really attractive place to live is next to the coast. Living near the ocean is what a lot of people do. 2/3 of the world's population or so lives on the coast, which means that a lot of people are continually exposed to this hazard. And the last one there is just related to the event itself. These are really powerful events, right? This is not something that you hear tsunami, I'm going to grab my surfboard and I'm going to surf the tsunami because that's going to be epic. It won't be. The force of this water is absolutely extreme, has more than enough capacity to pull people, boats, houses, cars, trees out to sea, fill these events with a bunch of debris that absolutely can do some irreparable damage. And so the turbulence of that water, the things that it carries, the force of it alone, most certainly is not something that you could deal with with our human strength, right? And so these factors result in these things being incredibly impactful events. And so we want to take a look at a few of these because studying the history of these events, right, knowing how these things are generated and the impacts that they have is certainly an important part, right, in our preparation for these events inevitably happening at some point in the future. So maybe through this lecture, you've been thinking, you know, or maybe you've already paused the lecture and Googled. If you have, that's wonderful. But if not, we'll answer the question, what it was the biggest tsunami in modern times? It was the biggest tsunami in modern times. But we're going to talk to you about the 1958 Lituya Bay tsunami. Then we're going to talk about the 2004 Indian Ocean tsunami, which did an incredible amount of damage. And then we're going to talk about the 2011 Japan tsunami, which also experienced a bunch of damage and provides us with a really good contrast, right? Or a really good point of comparison as to that illustrates how important early warning systems are and preparation in general are, right? But also how the impacts of these events, even though you might be really well prepared or think you're really well prepared, how the impacts from these events can still be massive, can still be absolutely massive. All right? All right. So let the fun continue. Let's talk about Lituya Bay. Lituya Bay there in Alaska is a glacial bay, glacial embayment, also known as a fjord, that's surrounded by really steep slopes. So as glaciers have moved through this area, we can see two of those glaciers are still here, right up here and right up here. These glaciers at one point converged here with some other smaller glaciers here in the adjacent slopes, and then eventually fed out in this area. Some of these structures that we see out here surrounding this embayment are actually sediments deposited by the glacier that used to move through this area. So the glacier moving through this area certainly assisted in some erosion of this canyon, as well as some deposition, and produced these really steep slopes adjacent to this fairly narrow embayment. So we've got ourselves a fairly narrow body of water here. And adjacent to this narrow body of water, again, along these steep slopes here, and we can see this in this geologic map, there is a fault right here, a fault right here. This type of fault is called a strike-slip fault. Strike-slip fault. These faults move in a side-by-side fashion. You might remember our discussion of transform plate boundaries. Motion here, again, side by side, just like that, right? So that side by side motion along this fault is not itself enough to provoke a tsunami, but the stuff along that steep slope most certainly can provoke a tsunami, because that stuff spilling into this narrow embayment, most certainly can displace large volumes of water, of water there. And so surrounding this embayment, we're going to watch this video together here. We see evidence of several catastrophic events along the hillside. That is, people entering into this beautiful fjord noted, wow, the trees near the water look much younger, right? Much younger than the trees further away from the water. And there's a really marked line that differentiates these two populations in the surrounding vegetation. What's that all about? What's that all about? And so we're going to take a look at that here in watching this video together. So let me go ahead and get that pulled up for us here. All right. All right. Here we go.
Lituya Bay is one of my favorite places in the world. It's a magnificent landscape. There are mountains roaring up behind it. Glaciers come off those peaks right down to sea level. And you have a bay that is unique along this coast.
Plafka came to Lituya Bay with his colleague Don Miller in 1953. They came to survey for oil.
We didn't find any petroleum in Lituya Bay, but what we did find was something that happened on a cataclysmic scale, and we spent a large part of our time trying to understand it.
What these scientists discovered in the 50s was the evidence for a previously unknown force of destruction. The evidence lay not in the rocks, but in the trees.
One thing that was very peculiar is the fact that mature forests did not extend all the way down to the shoreline, as was true almost everywhere else in this general area. Instead, there were bands of younger trees below mature forest, and the line at which the trees of different ages joined, we call the trim line.
Nothing like this had been recorded before. They suspected the surviving trees from just above the trim line might contain evidence of what had happened many years earlier.
We cut selected trees, took samples from those slices and sent them to the Juneau Forestry Research Lab and asked them to count the rings and give us an analysis of just what happened to those trees.
This is a photo of a section of a spruce tree that was taken by Don Miller and George Plafka in 1953 in Lituya Bay. The tree was right above a trim line in the bay, and it tells a very interesting story. The early growth in this tree was very good, nice wide rings. All of a sudden, it changes. Something happened to it. Something must have hit it very hard on this side over here. There's a large scar.
The tree ring analysis showed a violent force had struck the entire shoreline of the bay. The forest looked like it had been hit by a giant wave. For the scientists, it seemed impossible. No wave in history had ever reached anything like this high.
There was some powerful force at work here that created a wave, possibly 150 meters high. That's equivalent to, say, the height of a 50-story building. And we just didn't have any idea of what could do that.
Even the most powerful waves, tidal waves, known to science by their Japanese name, tsunami, could not have created such destruction. This wave had been caused by something very different.
Well, we didn't know what caused the wave. We considered earthquakes, and the earthquakes caused tsunami, but those tsunamis are usually less than 10 to 15 meters, and here we have something that's 10 times as high as that.
All right, let's get our presentation back here. All right, there we go. All right. Well, Lituya Bay, interesting history in that this so-called trim line had been recognized for a really long time by visitors to the area. They noted this change in vegetation, and the Lituya Bay was just a little bit different with this change in vegetation, right adjacent to the coastline. But a beautiful fjord, and so people certainly started to call this place home. There are fish and things in here that certainly were an attractive resource as well. And through time, with people living in this area, they noted that sometimes there would be some relatively smaller tsunami waves generated by landslides in the surrounding slopes. But eventually there in 1958, what happened is that fault there running adjacent to the slopes there gave way. That fault gave way and released somewhere approaching an 8 magnitude earthquake. That earthquake, the shaking of that earthquake, dislodged a ton of rock in that adjacent slope. It likely also dislodged some of the materials from the adjacent Lituya Glacier. And so the sliding from both of these sources displaced a huge volume of water. So approximately 40 million cubic yards of rock, about 40, again, a cubic yard 1 yard by 1 yard by 1 yard. Picture one cube like that. Picture 40 million of them, right? Entering this narrow embayment all at once. That landslide triggered a really big mega tsunami. And the way it did this was not just by displacing the water, but actually by displacing and throwing that water. That is, as the stuff came into the water, it landed so quick, so fast, that the water didn't just lift and rise. It actually was airborne out underneath a portion of that wave, such that the height of this wave, right, the run-up elevation for portions of this wave may have been as high as 1,700 feet. Absolutely enormous amount of water moving through the embayment. People did lose their lives during this event. There are some eyewitness counts of this event. But again, largely constrained to Lituya Bay. This is not something that's going to make its way across the entire ocean here. This is an event that would have stayed constrained to Lituya Bay. And again, this wouldn't have been the first of these events. Those scars that we were seeing in the side of the mountains there that you can see in this upper image here, and were discussed in that video there, those scars most certainly produced by similar events over the history of this embayment. So a really interesting geologic setting producing this really interesting, unique, and deadly wave. But let's talk about now a tsunami generated by the movement of tectonic plates. In 2004, there was a massive tsunami generated in the Indian Ocean. Happened on December 26th, Boxing Day. Sometimes this is referred to as the Boxing Day tsunami, and resulted in a huge number of casualties and injuries and damage done. This tsunami, unlike our Lituya Bay tsunami, was not caused by a landslide, but rather was caused by that exact action that we talked about of that overriding plate being flexed at the subduction zone, that subduction zone eventually tearing, right, giving way, rupturing, right, and then portions of that ruptured sea floor dislocating or disrupting then all that water that overrode that zone, and then sending that energy then from that source. So that source there is the interface between the Austro-Indian plate and the Sunda microplate. This subduction zone, right? This subduction zone here. So here we are, here's the Indian subcontinent. So we're just a little ways east of that near Sumatra. And so the run-up elevation for this tsunami was not the 1,700 feet of our Lituya Bay incident, but still really substantial. 100-foot run-up elevation for this event. All right. And so the geologic setting for this again is that we've got here the India plate here. So here's our India plate is descending here, descending into the mantle, right? So subducting, right, at what is called the Sunda Trench. And we know from our plate tectonics discussion, you see a trench, you know that's going to be a subduction zone, right? That's going to be some sort of convergent plate boundary, right? This lies to the west of the earthquake's epicenter. So this epicenter of this earthquake was down below Earth's surface, still at the subduction zone, right? But we got to think about this plate boundary three-dimensionally, right? So these are occurring at some depth, right, below Earth's surface, but still along this subduction zone, right? So this trench is the surface expression of this subduction zone. But as these little triangles indicate, here's our overriding plate, here's our subducting plate. That interface continues down below Earth's surface in this direction. And this is where we got this main shock along with all of here's the main shock along with all of these subsequent aftershocks after this event. The main shock of this earthquake is estimated at somewhere around a 9 magnitude earthquake, a 9. to generate earthquakes this large, you generally need a convergent plate boundary, or you need convergence to do that. You've got to have some convergence to do that. Transform plate boundaries, divergent plate boundaries, we'll get earthquakes at those locations too, but they will not be this large. The depth of this earthquake, again, significantly below Earth's surface, around 30 kilometers depth, and then again off that west coast of northern Sumatra. The portion of the seafloor that was deformed during this event was about the size of California. Around 745 miles of seafloor was moved, with portions of that seafloor being moved upwards by about 100 feet. 100 feet. So again, you picture something, you picture a plate boundary about the length of the state of California moving all at once in some places by 100 feet, and picture the amount of water that would be over that. And it is absolutely enormous. So with that disturbing force, this is a really interesting model that shows how that energy then propagated its way through the ocean, right? And so you can see there in the colors there, the hotter colors there, the reds and yellows, that main pulse of energy, right? That main pulse, and you can see that energy dissipating as it moves across the Indian Ocean here, right? As that energy disperses itself over a wider area, that energy generally decreases the further it goes from the source. But notice, right, that portions of Eastern Africa most certainly experienced this event, along with, again, portions of India, obviously Thailand, Sumatra, and other places surrounding or within the Indian Ocean here. But there's something else I want to point out about this this image, and I want everybody to take a look at the way these waves are moving, right? So in our waves discussion, we talked about refraction, right? The bending or turning of waves, right? And then diffraction. Diffraction being the way that waves are bent as they move past objects out in the open ocean, right? The way that they're reshaped by their movement past those objects. So we discussed that in terms of wind waves, but they apply here as well. And so as you notice, as this wave moves its way around India, right? You notice that it is turned, it's refracted as it moves past these islands that we can't even really make out in this portion of the Indian Ocean. We can see that those islands are most certainly resulting in diffraction of those waves. And just like we talked about for wind waves, we note that we get some reinforcement of wave crests that can be really, really significant. We can see this right here. Watch this diffraction. There, those crests reinforce. And then notice that there just happened to be another island, right, in that area of reinforcement. That is really unfortunate because, again, that reinforcement, just like with our wind waves, results in these waves being together larger than they were separate. I bring this up to note that these waves move through the open ocean impacted by things that are very similar to our wind waves, which means depending on where this energy begins, where it's coming from, the impacts of that event can be either made worse or could be made less significant simply by happenstance, the shape of the coastline, where a particular beach happens to be. It's really a bit of a roll of the dice in that you can have areas that are heavily impacted by a tsunami that are in very close proximity to areas that may experience very little damage at all. I also want to point out that just like we talked about with our wind waves, and we looked at waves crashing against the jetty at places like the Wedge and reflecting off of those, tsunamis can do that too. And if you look here, right here east of India, here we can see that these waves, if you notice, they're bouncing around in here for a little while, right? We see these waves kind of bouncing around. We see these colors kind of flaring up here and there for some amount of time following this event. And that is, again, because these tsunamis are not just single waves, right, that hit the shore and then are done, right? They can stick around for a while. And again, that energy then reflecting and refracting can result in multiple pulses of these events. And so it's really important in these events that everybody get the all clear before they come out of their safe areas, right? Before they leave any safe area, definitely want to have that all clear, because you could go down and try to help somebody or try to get some belongings or do something, right? And then get caught up in the next pulse of energy from this event. So when these things start, you really don't have much time. This is an interesting graphic from NOAA that shows the travel times for these various waves. And so we see that there near Sumatra, these waves approach and get there really fast following the earthquake. And this is a really, really dangerous aspect of these events for communities that are adjacent to these convergent plate boundaries, is that this 9.0 earthquake itself can be very destructive, most certainly would be felt. And so in that event, the earthquake itself may cause damage, right? May cause people to need help, things that delay necessarily the ability to go and get to high ground and get away from the approaching tsunami. So again, these areas that are adjacent to these convergent plate boundaries will have very short notice. So one of the approaches for the communities that live adjacent to these convergent plate boundaries is to do routine drills for what to do following an earthquake, with the intent being there to educate the community such that they know if there is an earthquake, the next thing they need to do after drop covering and holding is get to high ground, right? That is the next thing, because what you may experience thereafter is a tsunami. But again, these tsunamis are traveling exceptionally fast, hundreds of miles an hour. And so they were able to approach places like Sri Lanka, the Indian coast there, in just 2 hours time. They made their way across the entire Indian Ocean to portions of Eastern Africa there in about 10 hours time. So very little time all around to do anything other than really get out of the way, right? That these things are coming. All right. As we noted when we were talking about how to describe a tsunami, oftentimes, again, the initial sign of this tsunami, or of a tsunami approaching, is a rapid receding of the shoreline. And we certainly saw this during this event. This is the image on the left here is an image from a coastal portion of Sri Lanka during just normal wind wave events. Here, this image on the right captures these rapidly receding shorelines as that, shoreline as that tsunami is approaching. And so the next time you're at the beach, I sure hope I don't ruin your time in this discussion and thinking that every wave that comes up as it rolls back, here comes the tsunami, because that is not the case, right? And what we're talking about here is a rapidly receding, very distinctively receding shoreline that will be coupled with things like massive rip currents, which you're seeing here. You would likely see newly exposed seafloor. That is seafloor that's not typically exposed through the day. This is going to happen over the course of maybe minutes. It's going to be very, very fast, these events. And if you see that, if you're ever somewhere where you start to see that, you do not want to run out to those newly exposed areas. You want to go the other way, because again, it's not going to be that big towering wave over the city that is going to be that distinctive, right? What you're going to see quickly after these receding shorelines is then that that wall of water start to rise very quickly, and you don't want to get caught in that. You want to get to high ground, right? So just to give you an idea of how far inland these things can reach, here's a portion of the shoreline impacted by this event. Here's a before and after. Those purple shaded areas there being those areas that were inundated by the by the tsunami. And as we discussed, these waves, right, they're refracted and diffracted, just like our wind waves are, and thus they move their way inland in sometimes different directions and impact portions of the coastline in different ways. Sometimes different portions of the coastline may be impacted in different ways because of their topography. And so what we see here is a great example of that, in that we've got these rivers coming in. So we've got these relatively low-lying areas where that these rivers have carved. Look at how far these tsunamis were able, or the tsunami was able to reach, right? Versus some of these areas that have a little bit steeper topography, right? Some of these little steeper topography areas here adjacent to the coast, the inundation distance is not so great, right? And so, again, these waves and the amount of damage they're going to do to a specific area, right, is dependent on a number of factors that oftentimes cannot be predicted, all right? But these events are particularly devastating. I think that this image does a really powerful job, or sends that powerful message of how powerful these events can be. We've got a before and after for this community here in Indonesia. Those structures completely wiped out. This was a tremendously impactful event. An estimated 200,000 people lost their lives, maybe as many as 350,000 people. 125,000 people injured, approximately 45,000 people missing, and importantly, another 1.75 million displaced. Surviving this event alone, right, was not the only challenge. That is not just surviving the rising waters from this event alone was not the sole challenge. When this water floods the interior or these coastal communities here, what they also do is they shut down utilities. They take sewage and mix it with drinking water, right? They expose a lot of people to a lot of nasty stuff. And that means that in the days, weeks, months, years that followed, these impacts from this event could still be felt. And so this is not simply just avoid the water. There's a long period of after effects from these sorts of events. So estimated economic impacts from this event, about $4.5 billion in Indonesia, nearly $9 billion worldwide. Environmental impacts from this event, lost habitat, contaminated freshwater supplies, right? So you've got to get those freshwater supplies back, and you've got to do it fast, but you got to do it such that that water is safe to drink, right? Otherwise, that's a pointless endeavor, and that's a real challenge. And so along with a bundle of others, as we oftentimes see associated with natural disasters, environmental impacts can linger for a long time as an area recoups from one of these events. It's a great example of just that, is this Indian Ocean tsunami. Let's move forward in time a little bit to 2011. The island of Japan also sits next to a large convergent plate boundary. This convergent plate boundary is something that's well known, well understood, and most certainly has produced recorded earthquakes, or excuse me, recorded tsunami events and earthquakes over Japan's long recorded history. In 2011, there was a large earthquake along a subduction, or the subduction zone there, right adjacent to Japan. Estimated again around a 9 magnitude earthquake there on March 11th. This was triggered then by subduction of our Pacific plate right here below the island of Japan. And so this fault had produced problems for the island of Japan several times, most recently at about 869 AD, and has a known recurrence interval of events. So that is an estimated how often do these things occur of about 1,000 years, right? So this area was maybe a little bit overdue for one of these events. And so knowing that this event was potentially going to happen, right? Japan most certainly did have early warning systems in place. They had drills done where people knew what to do in the following an earthquake event in the area, particularly in coastal communities. They had plans in place. We're going to see that had a huge impact on the outcome of this event. So this event, maybe not as large in terms of rupture distance as what we saw there in the Indian Ocean. We've got about 20 to 26 feet of upthrust or upward movement of that overriding plate over a distance of about 180 kilometers or so. But again, with this boundary so close to the island of Japan, that gave really short notice for people to get out of the way of the pending tsunami. But they knew what to do, and so they did it, right? So with about 10 minutes warning from the earthquake itself and warning systems positioned on the island of Japan, people were able to get to safety. Not everybody, right? Not everybody. About 130-foot run-up elevation here in Japan. But again, compared the number of people that lost their lives in this event, about 16,000 dead, 6,000 injured, and around 2,500 missing, right? So a significant reduction, order of magnitude reduction in the number of lives lost during this event. But also notice the economic damage from this event. About $200 billion in economic damage from this event. And that is in part because of the amount of development that was present along this portion of the coast. One of the most famous aspects of that development was the construction of nuclear reactors at the Fukushima Daiichi and Daini power plants there along the coast of Japan. Nuclear power or generating facilities are oftentimes positioned in association with large amounts of or large water supplies. And again, we know that's because water has a high heat capacity. So it's oftentimes utilized to cool the reactions that are occurring and also as the source of the material that's needed to turn the turbines, right? So we pull that water out of the sea, that water is heated. It turns to vapor and steam and turns turbines that generate energy. So having these things adjacent to the coast, not rare. And in fact, here in Southern California, we have our own examples of nuclear reactors adjacent to the coast. You just got to go down that 5 freeway there near San Onofre, and you'll drive past some nuclear reactors at the San Onofre nuclear generating facility. That facility is being shut down and dismantled, but was operational for quite a while, and again was utilizing that seawater to assist in the process of making energy. So these facilities, much like our facilities here along our coast, were considered or were constructed with the possibility for one of these events to happen at some point in the future. And so there were emergency systems put in place at this nuclear facility in the event of an earthquake and a tsunami. So immediately following the earthquake event, what these facilities did was they shut down. They shut down immediately following the earthquake, 11 reactors. 11 reactors. When they shut down, what they run off of or what they have going there are backup power systems, right? Backup power systems that help to, again, you can't just take these reactions and just, it's not a light switch, right? You still need some power there to ensure that these things are being cooled continually and appropriately. But what happened was that the seawalls there that were put in place to help protect these reactors were shown to be insufficient. And those emergency power supplies were overwhelmed then by the water flooding these facilities. And so they shut down. So the reactors themselves started to melt down. And there were several explosions at these facilities that resulted in the release of some radioactive material to the surrounding environment, into the atmosphere. And a really remarkable story came out of this, is that a group of individuals, largely elderly individuals, many of whom were retired, following this event, they immediately recognized what the threat might be to these nuclear facilities. And even individuals that were retired volunteered to help address the problem. These individuals are commonly referred to as the Fukushima heroes. The use of elderly to go in and address concerns within this area of potential exposure was not just unguided, sort of just jump in and go for it thinking. There was some thought that, by the time that for older individuals, by the time after being exposed to radioactive material, they might be concerned about things like cancers, certain types of cancers and things, that would be past their lifespan anyways. But it is a really remarkable thing to see these individuals recognize the potential threat and step up, right, and absolutely work hard to save the environment and lives. It's a really remarkable story, and there are some truly remarkable stories embedded within the Fukushima heroes. If you get a chance to read about them, they're a remarkable set of individuals. So again, right, while the loss of life may have been reduced, we still see exposure to this hazard can have disastrous consequences, even in areas where we think that we're prepared, right? So in working to prepare for these things, what do? Right? Well, we work hard to better understand these sorts of hazards so that we can understand the true potential for what they might bring, right? And so, right, we might think to ourselves, well, it'd be really handy if we could predict where and when tsunamis will happen, right? So we mentioned, well, we can't predict tsunamis in terms of, we'll be able to say, in October of 2025, there's going to be another tsunami, so let's get ready for that. Or in 2 weeks, there's going to be a tsunami, let's get ready for that. We can't do that. Very similarly, a very similar story for how we have to deal with earthquakes, right? We have to recognize where these conditions exist and then look at the potential areas exposed to this hazard, right? That is, we have to look for the potential susceptibility of an area to tsunami based on geologic conditions in the surrounding area. Is there potential for landslide? Is there potential for calving glaciers? Is there potential for plate tectonics disrupting the shape of the seafloor? And if there are, absolutely, we need to prepare ourselves. We have to better understand what the size of the tsunamis that can be produced by those events, those communities that we may need to notify, how we're going to notify them. Those are all big elements of preparation. But at the core of that, at the core of all of that, is certainly connecting people to systems, warning systems, that give adequate notice of when one of these events might be coming, right? So there's a number of resources out there available for doing exactly this task. We're going to go ahead and look at the Pacific Tsunami Warning Center and what they do in a video published by their team. So let's go ahead and do that. All right, here we go.
It's 8 a.m. in northern Chile. As people on shore begin their day, 25 kilometers below the Earth's surface, tectonic plates shift in a massive earthquake. Immediately, seismographs detect this activity, and computers begin determining the quake's epicenter and magnitude. Within seconds, people feel the powerful shaking, strong enough to knock them to the ground and damage buildings. This is a warning sign of a possible tsunami. Without waiting for an official tsunami warning, people start evacuating to high ground or the top floors of tall buildings. A tsunami is a series of potentially deadly ocean waves, created by a powerful undersea earthquake that can last for hours. 76% of the world's deadly tsunamis have occurred in the Pacific Ocean. In 1960, a magnitude 9.5 quake off Chile's central southern coast caused a tsunami that claimed lives across the Pacific Ocean. Sensor data from a global network is continuously transmitted to the tsunami warning centers in Chile and Peru, as well as the Pacific Tsunami Warning Center, PTWC, in Hawaii, where duty officers assess the tsunami threat. The PTWC serves as the operational headquarters for the International Tsunami Warning System for the Pacific. The PTWC analyzes data and issues tsunami threat advice for countries throughout the Pacific Ocean. This information is vital for nations that are too far away to feel the earthquake, but may be in the tsunami's path. The Pacific Tsunami Warning and Mitigation System is coordinated under the UNESCO Intergovernmental Oceanographic Commission. It covers 46 countries of the Pacific Ocean and its marginal seas, and was started in 1965 in response to the deadly Chile tsunami of 1960. Early readings indicate the earthquake is at least a magnitude 8.8 and located off Chile's northern coast. Later readings will ultimately show it to be 9.5. This shallow undersea earthquake creates a giant tsunami. Officers at the tsunami warning centers in Chile and Peru issued tsunami early warnings to all coastal towns in the vicinity. The tsunami is expected to arrive in as little as 10 minutes in Chile and 45 minutes in Peru. Emergency responders and news organizations act on the tsunami warning and immediately announce the evacuation. The PTWC completes its initial earthquake analysis and issues the first tsunami threat bulletin to all countries in the tsunami's predicted path. Officers from the PTWC call the tsunami warning centers to advise them on their forecast. Some countries have their own tsunami forecasting capabilities, while others rely on the PTWC's tsunami advisory services. Early warnings with accurate tsunami forecasts depend on contributions from all countries and the free and open sharing of real-time seismic and sea level data. The PTWC forecasts that tsunami waves of 5 meters or more will arrive in Hilo, Hawaii and Samoa in 14 hours, and in Japan in 22 hours. The PTWC issues its second bulletin with predicted wave heights to all countries. The first of many tsunami waves strike the Chilean coast. Fortunately, due to regular tsunami evacuation drills and the early response, no one was in the danger zone when the waves crashed ashore. There are no casualties. The PTWC reports on observed waves for Chile. The third wave was the largest and arrived 30 minutes after the first. The PTWC monitors tsunami threats and advises countries across the Pacific. Each nation issues its own tsunami warning and guides its own emergency response. In Samoa and Hawaii, tsunami warnings are issued and evacuation begins. Local authorities quickly spread the word about the tsunami alert and carry out their response plans. The PTWC continues monitoring and issuing updated bulletins and reports. 14 hours after the earthquake, the tsunami strikes Hawaii and Samoa. Thanks to status bulletins and advice from the PTWC, these areas have fully evacuated. The natural disaster causes extensive property damage, but no lives are lost. The tsunami sweeps across the Pacific Ocean. Tsunami warning centers on the western side of the Pacific issue warnings in preparation, while emergency management authorities in those countries determine areas of evacuation. Hawaii and Samoa have canceled their warnings and deployed search and rescue teams. Chile and Peru begin the process of digging out from their earthquake and tsunami damage. This scenario was fictional and meant to illustrate how all the elements of the Pacific Tsunami Warning System work together to save lives across the Pacific in the event of a tsunami. The Pacific Tsunami Warning System is an evolving system that saves lives. Only with ongoing long-term support can the PTWS stand ready to warn nations in time to take action. No one knows when and where the next deadly tsunami will occur. But we must remain prepared, for it could happen today or 50 years from now.
All right. All right. So the PTWC, again, doing some really, really important work there to give people as much advance notice as possible to get out of the way. And so, fortunately, we live in California, so nothing to worry about, right? Right? Wrong, absolutely. So here again, adjacent to the Pacific Ocean, we most certainly are exposed to and have observed tsunami in our area. And in fact, during that 2011 Japan tsunami, those tsunami waves were significantly reduced in size from what was witnessed in Japan there. But portions of coastal California most certainly impacted by those waves. There's some amazing video from Dana Point here with water rushing into and out of the harbor. There's some amazing video from up near Santa Cruz of waves washing through the harbors there and damaging boats and docks and those sorts of things. And so we are exposed to seismic hazard, or excuse me, tsunami hazard. But I want to mention that our tsunami hazard is not necessarily associated with movement along faults in our area. We have this really tremendous plate boundary here in Southern California, the San Andreas Fault. The San Andreas Fault. The San Andreas Fault is, as we discussed during our plate tectonics lecture, a transform fault, a transform plate boundary, which means that that motion is side to side, side by side. Also, that San Andreas Fault is on land, right? So that San Andreas Fault is just a little bit east of campus there, near the San Bernardino and San Gabriel Mountains, then all the way north up through San Francisco. So it travels largely on land, right? So both of those factors mean that movement along the San Andreas Fault are not likely to directly cause a tsunami. I will note that there are numerous faults here in California, particularly here in Southern California, that are off the coast, off our coastline here. Several faults move off of our coastline, or are present off of our coastline, but the majority of those faults too are strike slip or transform faults, that side-by-side motion. So we don't get that seafloor displacement that we need to cause a tsunami. Movement along those faults might dislodge rock off of maybe Catalina, similar to our Latuya Bay sort of incident. Something like that could generate waves, but movement along these faults alone are not going to be enough to do it. However, again, the Pacific Ocean having so many convergent plate boundaries, or so much of its perimeter surrounded by convergent plate boundaries, we certainly have opportunities for displacement of the seafloor in those locations. And those locations can certainly send significant tsunamis our way. So if you take a trip down to places like Orange County, you will see around town, you will see a number of, especially near the coast, tsunami warning signs. They also have tsunami warning sirens around town. And a little bit of a funny aside was that I was living in Orange County for a little bit of time and was doing a little bit of work at home when we had just moved out there. I was by myself, and it was middle of the day on a Friday, and suddenly the sirens, the tsunami warning sirens, started to go off, and I lost it. I was super nervous. Was frantically trying to figure out what was going on there online, and there was no sort of immediate anything on the news or anything going on that mentioned anything about a tsunami. And then I went to the city's webpage, and evidently they test their sirens once a month. I forget which Friday of the month, which day of the month it necessarily was or is now, but it happened to be the day. And so they were just testing the sirens. A little bit of a notice might have been nice, but that most certainly was a little bit thrilling, to say the least. But those sirens, those signs, they are there for good reason. And that is because, again, tsunami can happen in our area. And so one of the things that various coastal counties have done is taken an assessment of their tsunami hazard and evaluated which areas might be potentially within an area that would be inundated by an approaching tsunami. And so recently, just recently here in July 2021, these maps that Orange County has drawn have actually been revisited and refined a little bit based on the current understanding of tsunami hazard. They've also taken these boundaries and put them into a GIS style server, which GIS information, let me go ahead and pull this up for everybody. GIS, this spatially referenced database type system, allows us to put these boundaries of what would be a tsunami hazard area, and then those areas outside of that hazard area, so that we know, hey, do I live or work in any of these hazard areas? If I do, now I can plan an evacuation route. So looking at this map, as these instructions suggest, this map, these yellow areas show areas that may be potentially inundated in a predicted tsunami here. So we can see, particularly here in low-lying areas in Orange County, that inundation can reach quite far, right? And so what you might do, say if you were working or living here in these areas in Huntington Beach around the Bolsa Chica wetlands here, you would say, okay, I live in these houses here off of Sea Point. So I'm within the hazard area. So during a seismic event or during a tsunami event, I need to get out of there. Maybe I live right here. I'm going to go ahead and travel up Garfield here to some high ground to get out of the way. And so this is a really neat interactive database. You have the link for it there in your slide deck, but it speaks to really the one thing that you can do to get out of the way of the, to survive these events, and that is get out of their way, right? The way you get out of the way for a tsunami is you go inland and you get up, right? So you're racing inland to get further in from that inundation distance, and you're getting up high in elevation to deal with that run-up elevation there, right? That's the goal. So those tsunami evacuation routes that you might see posted around town, that's their exact goal, is to get you to high ground as far inland and as quick as possible, right? You can imagine it being a little bit chaotic, right? With millions of people trying to navigate these routes. So having investigated this prior to one of these events happening as part of preparation, it absolutely can mean the difference in saving lives, all right? So again, these sorts of maps exist for various counties with routes and all sorts of things. This is just one example, most certainly highlighting that these areas most certainly may be impacted by one of these events. All right. Awesome. So preparation is key there, right? So in summary, we focused a lot on tsunamis today, right? But our long waves are our great waves, right? These waves with incredibly long wavelengths, including things like seiches, right? And our tides that we're going to discuss here not too long, right? These things are our great waves. Tons of energy involved in these things. And with tsunamis, that tons of energy reflects or manifests itself as tons and tons of damage and death and destruction. And so tsunamis generally related to geologic activity, things like shifting plates or moving rocks. They're super, super fast. They move incredibly quickly, able to traverse entire oceans in the matter of just a few hours. And so protecting these coastal areas really requires these early warning systems and other preparation events that you might do, again, to be ready for when one of these events may occur. All right. Awesome. All right. So with that said, that concludes this discussion. But it doesn't, again, have to conclude our interaction on it. If you have any questions at all, it's what I'm here for. Please don't hesitate to reach out. It's always wonderful to get to talk to you guys. So please don't hesitate to get a hold of me. I hope that everything is going fantastic. I wish you all the very, very best. Hope you have a great, great day. Be safe out there, and we will talk again very soon. All right, take care of yourself.